Let us start by understanding loss functions. First of all, let us have a look at mean squared error with the sigmoid activation. To understand this loss function, we are going to run a simulation. In the simulation, we'll have one single neuron whose weights have been randomly initialized. So the W is 0.6 and the bias is 0.9, which is randomly initialized. Next, the input to this neuron is always going to have the value 1 in our simulation. There is the sigmoid activation on this neuron and the output should always be equal to 0. This is what we are going to train the network for. Initially, with the random initialization, the output is 0.82. As we want the output to be 0, in a sigmoid function, the output is 0 when the input is minus infinity. To have the input to the activation function equal to minus infinity, we should have the weight as a very large negative number and bias also a very large negative number. Then only the output will be a very large negative number and sigmoid of a very large negative number tends to 0. So if we run a neural network, we use gradient descent to optimize W and B. The W and B should go down to very large negative values. Let's see what happens when we run this simulation. After we run the simulation for 300 epochs, you can see that the weight has become minus 1.28 and the bias has become minus 0.98. The output, it should have been 0, but because of gradient descent, it has not yet reached the local minima and the output is 0.09. If we have a look at the cost function, which was mean squared error, this is how the mean squared error looks while the network is being trained. So it reduces drastically in the beginning itself and then slowly it decreases to 0. So this is how the simulation looks. Let's run another simulation with slightly different weights and bias. So in our new simulation, the weight is taken to be 2 initially and the bias is taken to be 2 as well. What do you think will happen when we run this simulation? Will it take more time to converge to the value 0 or will it take less time? Intuitively, we think that as the error is larger initially, in the second case, the model should learn faster. So if you make a large error, you try to overcompensate for it and usually you try to learn faster. Initially, in our first simulation, the output is 0.82. Over here, the output is 0.98 and we are going to train it to output 0. Hence, ideally, the cost should decrease rapidly in the beginning and converge to 0 faster. Let's see what happens. After running the simulation for 300 epochs, you can see now that what we had expected, it did not happen. Even after running for 300 epochs, the output is still 0.2, which is much higher than 0.09. Also, the weights and bias are not that large negative numbers compared to the previous run. Having a look at the loss function, it shows that the loss value did not change for the nearly 150 epochs and then it started to decrease. This is a bit counterintuitive because if the cost was large initially, then it should have started decreasing faster. What we can see over here that the cost does not change for a lot of epochs and then it starts decreasing rapidly. Let us try to understand why exactly this happens. Before we go on to understanding this, let's just revise that the weight update rule looks like this. The new weight is the current weight minus learning rate into the gradient of the cost function with respect to the current weights. What it means is that the new weight is equal to the previous weight minus a small step in the direction of the gradient, opposite to the direction of the gradient. So now um, over here we can see that as the cost did not decrease initially, the reason must have been that the weights did not decrease initially. So if the weights do not decrease, then the cost function would remain the same. Now let's have a look at the weight update rule. So if the weights are not changing initially, it means that eta times delta C is very small. As we have kept the learning rate same in both the simulations, we can take out the learning rate factor. So what it means is that the gradient of the cost with respect to the weights is small during our second simulation, while it's large during our first simulation. Why is that so? I'll repeat. As the weights are changing drastically in the very beginning, it means that the gradient is larger. Over here, the weights are not changing, hence it means that the gradients are smaller. So let us have a look at the equation of the gradients to understand why exactly the gradient is smaller over here and why it's larger over here. First of all, let us have a look at how the sigmoid function looks like. So this is the graph of the sigmoid function. The mathematical equation of the sigmoid function is sigma of the z, which is the input, is equal to 1 by 1 plus e to the power minus z. So this is the equation of the sigmoid function. How does this look in a graph? Is shown over here. Let's concentrate on the derivative of the sigmoid function with respect to z. If you do the mathematical jargon, you'll be able to find out that sigma dash of z, which is derivative of sigma with respect to z, is equal to sigma of z into 1 minus sigma of z. Sigma of z is the sigmoid function. So I have written over here the derivative of the sigmoid function in terms of the sigmoid function itself. Let us try to understand this mathematical equation to better understand the sigmoid function. Derivative is the slope of the graph at a certain point. So let us concentrate on the derivative at the extremities, which is when z is very large in the positive or in the negative direction. When z is large in the positive direction, sigma of z is equal to 1. How is that possible? So when z is very large, e to the power minus a very large number tends to 0. Hence 1 by 1 is equal to 1. So sigma of z tends to 1 when z tends to infinity. Next, when z tends to minus infinity, e to the power infinity tends to a very large number. Now 1 by a very large number tends to 0. Hence sigma of z tends to 0. So let us have a look at the derivative. When z tends to infinity, sigma of z tends to 1. But 1 minus sigma of z tends to 0. Hence 1 into 0 is equal to 0. Hence the derivative also tends to 0 when z tends to infinity. Similarly, when z tends to minus infinity, sigma of z tends to 0. 1 minus sigma of z tends to 1. Hence 0 into 1, it tends to 0. So sigma dash of z tends to 0 when z tends to minus infinity. What this means is that if your z is large in the positive or the negative direction, sigma dash of z is 0. Let us try to understand how this affects our neural network. So first we calculate the derivative of the cost function with respect to our weights. So we have taken the partial derivative of the cost function with respect to the weight. Partial derivative, it means that we have kept all the other variables constant right now and are just differentiating with respect to our one weight. Over here, you can see the equation a minus y sigma dash of z into x. Now, what does a, y, z, and x mean? Though it's not necessary to understand the point, I'll just say it once. A is the sigma of z. So A is the output after applying the activation function. That is why A for activation function, and that is equal to sigma of z. Y is our target variable on which we are training our neural network. Sigma dash of z is the derivative of sigma function with respect to z. Next, we have x. So z is equal to wx plus b, and that is x, which is the input to our hidden neural network. So this is the variables of the equation. You do not need to remember what each variable represents. The important part is sigma dash of z. What it means is that if the derivative of the cost function with respect to the weights is directly proportional to sigma dash of z. So if sigma dash of z is very small, let's say it tends to 0, then the derivative also tends to 0. We have seen that sigma dash of z tends to 0 when z is very large. So when w is very large, sigma dash of z will tend to 0. And that is what was happening earlier. When initially the weights were very large, z was very large. Hence, the derivative or the gradient was very small. So the model was not learning fast. Ideally, we will want that our model, the derivative of the cost function with respect to the parameters, is independent of the sigmoid derivative, so that even though our weights are initialized by a large value, they do not tend to 0. The derivative of the cost function with respect to the parameters, it should not tend to 0. So this is what we ideally want. Can we achieve it? Let's have a look. We will now have a look at another cost function, which is the cross entropy loss function. The graph of the cross entropy loss function looks like this. So first of all, let us try to understand from the graph itself whether this loss function will help our neural networks converge to a good value or not. So first of all, the criteria of the loss function is when the output of the model is far away from the target, the value of the loss function should be very large, and when the output is close to the target, the value of the cost function should be very small. Is that possible with cross entropy loss? So let's have a look. When our target is equal to 0 and our model predicts a value of 1, that means the output of the model is very far away from what it actually should have predicted. Then you can see the loss value tends to a very large value. So this sounds good. And if the model outputs 0, then the value of the loss function is also 0. So this means that when the output is 0 and the target we are expecting is also 0, the loss has a value of 0. And if the target is 0 and the output is 1, then the loss has a very large value. Similarly, if the target is 1 and our model predicts 0, then the loss is very high. If the target is 1 and our model predicts 1, which is the correct prediction, then the loss is 0. Hence, this cross entropy loss, at least theoretically, should help our model converge. Now let's have a look at the mathematical formulation. This is the mathematical formulation of the cross entropy loss. So C equal to minus 1 by n, where n is the batch size, into summation of y ln a, where a is the output of the model and y is the target. plus 1 minus y into ln. So ln stands for the natural log, log to the base e of 1 minus a. A is the output of the model. So when we are doing a classification task, usually our target is just 0 or 1. When y is 0, then this term becomes 0, and what we are left with is just ln 1 minus a. The blue curve is the curve when y is equal to 0. So the x-axis is the output of the model, which is a over here, and the y-axis is the value of the cost function. So when y is equal to 0, our cost function is just ln 1 minus a. Hence, this is how the graph looks. When y equal to 1, this term becomes 0 because 1 minus 1 is 0. Hence, we are only left with the term ln a. So this is how the curve looks. Mind you, there is a minus sign outside. That is why the curve looks like this. So this is how our cross entropy loss looks like. Now, why did we introduce the cross entropy loss? So the interesting fact about cross entropy loss is, if we calculate the gradient of the cost function with respect to its weights, it comes out independent of the derivative of the sigmoid activation function. This is what we wanted to help fast increase the speed of our training of the neural network. And you can achieve that by using cross entropy loss instead of the mean squared error loss. So that is the advantage of cross entropy loss. Now, one fun fact, it was not like people just someone was sleeping and they thought, okay, let's try out cross entropy loss instead of MSE loss, and we'll get the derivative independent of the sigma dash. That is now not how people did this. What people did was, they assumed that there is a cost function whose partial derivative would give xj into a minus y. It would not have the sigma dash of z term. And they used integration to find out what should be the cost function so that this is possible. By doing the mathematics, they found out that if the cost function has certain structure like this, then the derivative of the cost function with respect to its parameters would be independent of the derivative of the sigmoid function. So that is how people found out that we should use this cost function if we are using the sigmoid activation function. So takeaway is that if you are using a sigmoid activation function, then you should use the cross entropy loss function to ensure that the gradient of the cost function with respect to its parameters is independent of the derivative of the sigma function. One thing which you guys might have a doubt with is that how come our cross entropy loss has two different graphs, one for y equal to 0 and another for y equal to 1. Actually, that's not surprising. Even the MSE loss has two graphs. When the target is 0, our MSE loss will look like the blue curve. And when the target is 1, our MSE loss looks like the red graph. And that's obvious because when the target is 1, the loss value should be equal to 0 when the model outputs 1. So this is how the graph looks like for the MSE loss with different targets. Next, let us have a look at another loss function, which is the log loss. I'll explain why are we having a look at this after we understand the log loss. So this is the equation of the log loss, which is just minus ln output of the model. Now, what does this mean is that the cost function is just negative of the natural log of the output of the model. This is only true when the output is 1. Otherwise, the cost is 0. So our model usually has 10 different outputs. If even one of them is 1, we'll take the cost of that particular output neuron to be equal to minus ln A. If the target of the output neurons is 1 at a position, the cost at that position is minus ln A. Otherwise, if the target is 0 for the other hidden neurons, then the cost is taken to be 0. Now, some of you guys might have the doubt, how do we train the other neurons if we are only training one of the hidden neurons in the output? So, to take care of that, we do not use the sigmoid activation function, but we use the softmax activation function. So what softmax means is that, let's have a look at the softmax function first, and then we'll try to connect it to log loss. So softmax has the following equation. Let's say we have 10 outputs in our hidden output neurons. What we do is we take e to the power all of the output of the hidden neurons. We add them up to get the denominator. We divide e to the power output of hidden neurons by the sum of all the hidden neurons taken e to the power. So this ensures that the output of our hidden neurons after applying the softmax is always less than 1, because e to the power z by summation e to the power z is always less than 1. Denominator is always greater than the numerator. We can have a look at this graphically. Let's say in our output neurons, we get the output 2, 1 and 0.1. After applying the softmax function, we take e to the power 2, e to the power 1, e to the power 0.1. We add them up, and then the output is e to the power 2 by e to the power 2 plus e to the power 1 plus e to the power 0.1. So take the e to the power 2 and divide by e to the power sum of all of them. So this will always be less than 1, and the fun fact is that if you sum all the outputs after the softmax activation function, the sum will always be equal to 1. So if we add 0.7, 0.2 and 0.1, we'll always get 1. That is because if you see at the equation, if you add all the individual outputs, the numerator will also become sigma of e to the power z. So the numerator and denominator cancel out and we'll get 1. So this is how our softmax activation function works. Now how does it work with the log loss? After applying the softmax layer, let's say our target looks like this. It is 0 at the first hidden output, 1 at the second hidden output, and 0 again at the third hidden output. We take the loss to be 0 directly for the first and the third outputs, and we calculate the log loss only on the first hidden output. So on the second hidden output by index 1. So we calculate minus ln 0.2 and we train our network. Automatically, if we are training the softmax function, so if we are training the second output to tend towards 1, then these values, the output of the first neuron and the output of the third neuron, would go down to 0. Think about it, why it might happen. You can pause the video and have a discussion or think about it, because this is important. So now I'll continue why this happens. First of all, let's try to understand whether this cost function actually will help our model converge the second value to 1 or not. So if the model outputs 1, then log of 1 is 0. So the cost value will be 0. Otherwise, if the model outputs less than 1, then ln of a value less than 1 is a negative number. So negative of negative, which is the minus sign outside, is a positive number. Hence, the cost function is positive for values less than 1 and 0 for exactly 1. This means that the model will help the output of this neuron converge to the value 0 of loss function, which happens when the output is 1. So we have confirmed that yes, this loss function will help the second hidden neuron tend towards 1. Automatically, because of softmax function, if the output of the second hidden neuron tends to 1, then the output of the first and third neuron will have to tend to 0 because the sum of these three hidden outputs tends to 1. I'll repeat, if the output of the second neuron tends to 1, the sum of these three is always equal to 1. Hence, these values, the first hidden neuron and the third hidden neuron values will automatically go to 0. And that is what we want our model to train on. If one of the hidden neurons is 1, then the model should output 0, 1, 0. So log loss with softmax is able to achieve this. But what is the problem with using cross entropy loss plus sigmoid? Also, does log loss take care of the problem which we faced with sigmoid? We faced the problem that in the derivative of the cost function, there was the sigma dash term. With log loss and softmax, we do not find such a term. So it's very similar to cross entropy loss plus sigmoid. So the moral of the story is cross entropy loss plus sigmoid is the same as log loss plus softmax. So why did we need two of these different kind of functions and activation function combinations? The reason being, sometimes you want the model to output probabilities. So what it means is that, let's say you want to classify whether this image is a cat or a dog. You want to interpret the output of the model in relatable terms. So if the output of the model has the sum 1, you can say that the model says that this image has a cat with X probability, and you can achieve that with softmax. If you used a sigmoid function, the output would not necessarily sum up to 1. Hence, you cannot say that the probability of this image being a cat is equal to the output of the hidden neuron. So that is one of the advantages of using softmax with log loss. Otherwise, there is no difference between the two combinations. So let's just revise once again of what we have learned till now. If we use sigmoid with MSE, the model converges slowly and it takes a longer epochs to train the model. If we use cross entropy loss with sigmoid, then the model converges fast and reaches better values of convergence. So never use MSE with sigmoid. That is the takeaway. Always use cross entropy loss with sigmoid. We also had a look at softmax with log likelihood cost function, which is equivalent to sigmoid with cross entropy loss. So that is the overview of what we have learned. Next, let us try to understand how to code the softmax plus log loss directly in Pytorch. As always, in Pytorch, such complicated functions are actually one-liners. So, Pytorch comes with its inbuilt softmax plus log loss, which is confusingly called cross entropy loss. So do not get confused. It's not actually cross entropy loss. It's softmax plus log loss, activation and loss function combined together into one function which is named cross entropy. To use it, you need torch.nn.functional.cross entropy and you provide the output and the target. Earlier, when you were applying the mean squared error loss, the target was in the one hot encoded vector. Currently, when you apply this cross entropy loss function, this function assumes that the target is in the categorical format. What it means is that the target has a value of 0, 1, 2, 3, 4 and so on. It is not like 0, 0, 1, 0, 0, 0. So you do not need to pre-process the target to convert it into a one-hot encoded vector. You can directly use the target returned by the data loader of MNIST. So this is how you implement softmax plus log loss in Pytorch.